second part of the definition is that you can actually control the material on that scale. So if I put, let's say, a device here, and 1 nanometer away from it, I want to put another device. Before 15 years ago, that was not possible. Today, we can do that easily. We can put devices 1 nanometer away from each other. These devices doesn't have to be new material, it can be normal material. So the definition is simple. New physical and chemical properties due to changing the size and the ability to control the material on that scale. These are the two things that define nanotechnology. A lot of you will hear the word nanomaterials. Nanomaterials are not new materials. Nanomaterials are the normal iron, copper, silver, gold, but are done on a nanoscale. So there's nothing new in terms of a new element or a new material. It's just a size. When you change the size, you get a lot of new properties. Now, the thing that I like about nanotechnology, what made me excited, very excited about nanotechnology, is that we don't think to solve a problem in a normal way. The whole thing about nanotechnology is that you're an engineer. I'm a chemist by training. When I was getting my PhD, the guy sitting right next to me was a software engineer. We had a pharmacist and we had a medical doctor. And all three of us were taking a PhD under the same professor. He's a chemistry professor. We got a software engineer getting his PhD from a chemistry department. You got a medical doctor getting his PhD from the chemistry department. And you got a pharmacist getting a PhD from the chemistry department. The thing that is very interesting is that we all have to talk with each other. We all have to solve the common problems together. And this is what is very interesting about nanotechnology. It is not just an enabling technology, it's a game-changing. You change the way you approach a problem. The simplest thing I can tell you, we had, in addition to me being in Nile University, I have my own company. And we were approached by one of the big oil giants. They were drilling offshore, so in the water. You, of course, all of you heard about the British Petroleum leak. That's an offshore drilling. What they were doing, they were drilling in the seabed, and the seabed was extremely hard. They had to change the drill bit every 2 weeks. Now, if you understand a little bit about the oil industry, to change the drill bit takes you a week. Each day costs the industry over $5 million if they're not working. So 7 days at $35 million lost money because we have to change the drill bit. So all the engineers, they were working on how to make the drill bit stronger. This is the typical way to think about the problem. The nanotechnologist says, no, you're looking at the problem completely wrong. You have reached the maximum in the hardness of your drill. What is the other side of the problem? It's the seabed. That's a rock. Can we change the properties of the rock? Yes, we can. Because we have material that can penetrate through the rock, make it softer. So instead of going changing the drill bit, I changed the seabed I'm drilling. Now this is what is innovation. Nanotechnology thinks always this way. And we know that we can change the rock because people in agriculture have done that using nanomaterials. So we took an idea from the agriculture industry, we use it in the oil and gas industry, and they're saving hundreds of millions of dollars every year. So this is what I mean by innovation. This is what I mean by fresh, innovative thinking. It is not the problem, it is your approach to the problem that matters. Nanotechnology enables you that. Now in 2007, worldwide, there was $13.5 billion in investments. The market size was $148 billion. Just to understand, in 2009, the entire income of Egypt from tourism was $10.4 billion. Again, in 2009, the entire income of all of Egypt from all of tourism business was $10.4 billion. 2007, the market size for nanotechnology was $148 billion. So that's almost 14 times more than what a country actually got in terms of money. So the market is here, it's not science fiction, it is happening. Now, what is the history of nanotechnology? So, very fastly, as you have to understand. The first ever mentioning of nanotechnology was in 1959, the very famous lecture by Richard Feynman, and he said there's a lot of room at the bottom, and that we can actually write the entire encyclopedia on the top of the pin. This was the first ever mentioning of going that small. Now, from 1959 to 1984, there was a lot of attempts to build instruments to allow us to manipulate and look at it, basically atoms and molecules. It was always a failure until these two guys, Richard Bennett and Robert Schroeder, they were working in IBM Research Center in Zurich. And they invented this machine that you see the schematic of it, abbreviated STM, forget about the name. What this machine allowed us to do is using a tip. It can scan the surface, pass a very small tunneling current, and we detect that current. Now, what is the data that we see out of it? All of us in chemistry, in high school and in the first year of engineering, you've always heard the word benzene ring, right? An alkyl chain. Now, are they really a ring? What you're seeing here is a monolayer, just a single layer of these molecules on the left, on the surface. These rings that you can see up there, these bright spots, these are the benzene rings. The chain, the dots right after each other, these are the alkyl chain. So basically we can actually see molecules and we can manipulate them on the surface. I'm not going to go too much into different techniques, but we have different techniques to allow us to see at the molecular scale. I practically like this one because this touches a little bit on engineering. What you see here is that on the left, this is another technique that we use. What you're seeing on the left is a topography image of the surface, how the surface looks like, height and depth. And on the left, it's pretty much flat. Now, if you look at the same surface using a different technique, on the right, you see it has different things. On the right, we're actually measuring friction of the surface. Basically, what you're looking at, this is an alloy. And what you're looking at is looking at the different grains of the different material on the surface. So although the surface is very flat, on the right-hand side, you can see that you actually have different friction areas, and this allows you to actually manipulate the alloys. I'm going to give one example of material. What I mean by changing the properties, changing the size, you change the properties. What you're seeing up there, this is what is called quantum dots, nanoparticles. Now these are made of semiconductor material most of the time. And what you're seeing inside the vial is exactly the same material but different size. And as you can see, on the left, it's the same material, cadmium selenide. Just forget about the material, it's a semiconductor material, like silicon. If you have silicon in here, you will have also different colors. The difference between the one on the left, the blue color, and the deep red color is the size of the particle. But it's exactly the same material. It's not a different material. So by changing the size, we change physical and chemical properties. Color is a physical property, but it's also related to the electronic structure, which means that the reactivity of these materials differ. So on the left, you have a particle like the one on top with a diameter of 1.9 nanometer, and on the left, you got a diameter of 6.9 nanometers. And as you can see, just changing the size changes the color. Now, I'm going to jump in right into a lot of different applications. So for the rest of the lecture, I'm going to show you some applications, how we make them across different industries. Electronics, telecommunication, water, agriculture, construction. These are the 5 things I'm going to show you some of the applications for. Now, how many electric engineers and electronics engineers are here? Wow, it's a whole lot of engineers. Okay. So all of you are familiar with this. This is a typical schematics of a device. You got a semiconductor material, you got a source and a drain, you got a dielectric material in between, and you got a gate. Now, all of you, of course, know Moore's law. Moore's law says that every 18 months, you're going to shrink the device, the size of your device,